Hello and welcome to Lesson 1 of Unit 6 Exponent Laws in our Grade 11 University College Math class. This is a really short unit. It sort of sets up the back third of our course, which is where we explore exponent laws and exponential functions and then an application of exponential functions, financial applications. So this first one is just to sort of put together just the exponent laws that we would expect you to know from grade 10. Whether you took the grade 10 academic or the grade 10 applied, this should be fairly familiar to you. So let's jump right in. We're going to start by just reviewing a little bit of terminology that I'll be mirroring over the course of the unit. The first is just the way that we talk about exponents. So the word that we want to use when we're talking about exponents are powers. So for example, you see down here, 3 to the exponent 4 is a power. A lot of times people will say 3 to the power of 4. Strictly speaking, that's not accurate. The power is the whole thing. Both the base and the exponent combined make up a power. Which leads me to the next part. A power is made up of two pieces. The base, which is sort of the larger number that takes the place, sort of sits on the bottom, I guess. And then the exponent, which is the number that's kind of a superscript, kind of hanging up in the air. The last piece of terminology I want to talk about before we jump in is just these two particular forms. So exponential form, which we've got right here, has our repeated multiplication in a power, meaning it's got a base and an exponent. Expanded form, however, is just another way of expressing what we're expressing when we use a power, and that's that repeated multiplication. So 3 to the exponent 4 would be 3 times 3 times 3 times 3. So this 3 shows up 1, 2, 3, and 4 times, and that's what provides us with the exponent part of our power. And if we were going to, like I said, write it in an expanded form, that exponent dictates how many of the 3's, our base, show up at all. Okay, let's just jump right into some examples. Our first example right here is already done for us in the note. So 5 to the exponent 4, the base is 5, the exponent is 4. That's already in your notes, pretty straightforward. Let's have a look at the next one. So you have 7 to the exponent negative 2. The base, of course, is 7. The exponent is negative 2. This next example, we have negative 5 to the exponent 4. Now the base is everything that's inside the bracket that the exponent is being applied to. So in this case, our base is negative 5, and our exponent, of course, is 4. That stands in contrast to the next example we're looking at here, which is negative 5 to the exponent 4. Now what's interesting about this one is that this 5 is the only thing the 4 is being applied to. Think of it more like negative 1 times 5 to the exponent 4. Something like that, where really the exponent is only being applied to the 5. That negative sort of hangs out front there. So in this case, our base is actually the positive 5. It would need to have, like in the example prior, brackets around it for negative 5 to be the whole base. And of course the exponent, once again, is 4. Let's have a look at this example over here. So you have 2x to the exponent 3. So again, let's consider that this is 2 times x to the exponent 3. So our base is actually only the thing that the exponent is being applied to, which in this case is x, and our exponent is 3. And our last example up here, we have 3x to the exponent 4. So what you'll notice is this entire term, the 3 and the x combined, that combined is having the 4 applied to it. So our base this time is the entire term inside the brackets, which is 3x, and the exponent, once again, is 4. A lot of 4's there. Okay, and that's just sort of a quick review of sort of terminology and how it works. As I said, we're going to move fairly quickly through this. This lesson is really meant to sort of help you realize that the exponent laws, they're not really laws, they're more like shortcuts. That if you can remember the shortcut, I guess we just call it a law, in that it's something easy for you to remember. So the first few we're going to write out in long style, and then we're just going to kind of power through it. So we're being asked to simplify the following products, which means sort of write them in as a single power. Now when we're talking about a single power, what we mean is one base, one exponent. So here we have 5 to the exponent 3. So the way that I sort of prove that this multiplying powers with the same base law is that I write this out. So let's just do 5 times 5 times 5, that's 5 to the exponent 3, times 5 times 5 times 5 times 5, which is 5 to the exponent 4. Now if we look at all those 5's being multiplied together, let's just change up our colors here a little bit. We've got 1, 2, 3, 4, 5, 6, and 7. So that's going to be 5 to the exponent 7. Now the shortcut, for people who remember, is that whenever you're multiplying powers with the same base, you can actually add these two exponents together for multiplying powers of the same base. And that's an important thing to remember, is that this only works when we're multiplying powers with the same base. So let's work that shortcut one more time. So if we have 2 to the exponent 2 times 2 to the exponent 3, it's going to be equal to 2 to the exponent 2 plus 3, which is going to give us 2 to the exponent 5. Now, students always ask me, is it okay if I sort of skip that middle step, that 2 to the exponent 2 plus 3? Absolutely. I always recommend students write it in their notes so that they have a reference if they should forget it. But I would say really a question like this, jumping right to 2 to the exponent 5 is totally fine. Okay, let's head on to C. Somewhere over here. Okay, so we have 4a squared times a to the exponent 3. So I'm going to write this one out stretched style. So that's 4 times a, that's the first one, and then we have a times a times a. Alright, so we're definitely going to have a 4 out there, and then we have, as before, 1, 2, 3, 4, and 5 a's. So that's going to give us a, oops, should keep my colors consistent, a to the exponent 5. Or, again, if we wanted to write it out like that, that would be 4a to the exponent 2 plus 3. Totally fine. All right, last example here. We have negative 2b times b squared. Now I want to point out, again, if you don't see an exponent there, it doesn't mean it's a 0. In fact, it means it's a 1. So we need to consider that when we're writing this out. So this is going to be negative 2 times b. That's our front monomial, and then we have b times b. So we can see that that's going to be negative 2b cubed. Okay, and then we have the expression of our law, and it's really nicely summarized right here, where if you are multiplying powers with the same base, keep the base and add the exponents. There we go. First one down. Let's move on to the second piece. Second piece is what do we do if we're dividing powers with the same base? So same idea here. I'm going to start as a proof of concept here at the beginning, and I'm just going to write this out in expanded form, which is 5 times 5 times 5 times 5 all over 5 times 5. Now what's cool about this is, just like any fraction, if you have the same, if you have equal factors in the numerator and the denominator, I could divide both the numerator and the denominator by 5, and that reduces one pair of 5s out of our numerator-denominator combo. I can do this again, divide the numerator by 5 and the denominator by 5. By doing the same thing to the numerator and denominator, we're maintaining an equivalent fraction. So now we're out of 5s in the denominator, so what we have left here is 2 5s in our numerator, 5 times 5, and 1 in our denominator. So we'll just leave that there. So that's going to be 5 times 5, which is going to be 5 squared. What we'll remember, hopefully the astute among us will remember, that when we're dividing powers with the same base, this is just the same as doing 5 to the exponent numerator exponent minus denominator exponent. Hopefully that rings a bell and it's familiar to you. Let's go have a look at example B. Example B, 2 to the exponent 8 divided by 2 to the exponent 5. So again, hopefully we remember. So this would be 2 to the exponent 8 minus 5, which would give us 2 to the exponent 3. Looking good so far. Hopefully that's making sense. Let's go tackle C. C's over here. This is just written in a different way. But again, as long as we remember that when we are dividing these powers, it's okay to subtract the exponents and keep the base. So in this case, we'd have our base, and we would subtract our exponents, and that's going to give us 4 to the exponent 2. Okie doke, let's try the last example here. There's D. This is 3 to the exponent 7 divided by 3 to the exponent 2. Gives us 3 to the exponent 7 minus 2, or 3 to the exponent 5. And then a little summary down here of our law, so to speak. If you're dividing powers with the same base, you keep the base, subtract the exponents. And that's the way it works. Hopefully this is looking good. we're going to stop the video here, and then we're going to do power of a power and then the application stuff that follows it. We should be able to finish all that up in the next video. So that's the end of part 1. We'll see you in part 2.